Welcome back to xnoesis, your sanctuary for deep thought and peaceful rest. Tonight, we're embarking on a journey, not just into the depths of sleep, but into the profound mysteries that whisper from the cosmos. This is a story about two extraordinary celestial visitors and how they've fundamentally reshaped our understanding of the universe. You may remember our first guest, the enigmatic Oumuamua. When it arrived silently in 2017, this needle-shaped object, accelerating without a visible tail, it genuinely baffled us all. It was strange, perplexing. It broke every rule we thought we knew about space rocks, a true cosmic anomaly. Its fleeting visit, however, wasn't just a puzzle. It was a profound call to action. It led to the creation of Atlas, our global network of watchful eyes, designed to ensure we'd never be caught off guard again by such a visitor. And now, in July of 2025, that very network, Atlas, has unveiled something new, something remarkable. A celestial guest designated 3I Atlas. This new discovery, this active interstellar comet, it doesn't just add to the mystery. It actually changes everything. It makes Oumuamua, in retrospect, seem almost ordinary. So, settle in as we unravel the cosmic secrets of these interstellar messengers. So, let's get started. Back in 2017, in the quiet solitude of that year, a visitor arrived from the unfathomable darkness between the stars. It was like an emissary from a place so distant, its origin is still a profound mystery. A whisper from another son's family. This traveler, this ghost in the cosmic night, it shattered every rule we thought we knew, every comfortable assumption we held about the nature of space rocks. It wasn't a familiar potato-shaped asteroid, nor was it a brilliantly hazy comet, trailing a tail of vaporized ice like some kind of celestial banner. No, this object, it was a needle of darkness, a shard of the unknown, and it was racing through our solar system at a velocity that's just hard to comprehend. Over 50 kilometers every single second. Imagine the quiet hum of the Earth in its orbit, and then this silent, cosmic bullet piercing our celestial neighborhood. Yet, its speed was only the first line in a story of immense strangeness. It was accelerating, pushing ever so gently against the sun's gravitational pull in ways that should have been impossible for a seemingly inert piece of rock. There was no tail, no visible outgassing, no telltale cometic glow to explain this ghostly push. There was only a dark shard tumbling end over end in a silent 7.5-hour pirouette through the void, moving faster, much faster, than anything we had ever witnessed originating from within our own solar system. This single, fleeting encounter was a profound awakening. It was a message in a bottle from the galactic ocean, and its arrival marked not an end, but a beginning. You are about to witness how that first, deeply mysterious visitor became the catalyst, the spark that ignited a revolution in how we watch the skies. It led us to construct the most powerful, most vigilant sky-watching network ever created, a global sentinel against the unknown. And you will journey with us to the quiet nights of July 2025, when that very network, born from the mystery of the first traveler, unveiled something new. Something that makes that first, enigmatic object seem, in retrospect, almost ordinary. Prepare yourselves for a journey into the deepest questions of our cosmic origins. We begin. The 19th of October, in the year 2017, stands as a quiet but monumental turning point in the human story of the cosmos. On that day, the universe gently peeled back a curtain, revealing a truth we had long theorized but never actually witnessed. On the serene volcanic summit of Haleakala, on the island of Maui, An astronomer named Robert Warwick was engaged in the nightly ritual of his profession, a patient and meticulous vigil. He was doing what astronomers do on any clear night, scanning the vast, silent tapestry of the stars as captured by the Pan-STARRS telescope. He was searching for the faintest of movements. You know, those tiny, wandering dots of light that tell you something is much, much closer to home. The Panoramic Survey Telescope and Rapid Response System had captured something, a flicker of motion against the static backdrop of impossibly distant suns. At first glance, it seemed unremarkable, just another space rock, a lonely asteroid drifting through the familiar, well-mapped territory of our cosmic neighborhood. It was just an anonymous point of light on a computer screen, one among thousands. But then, the meticulous work of measurement began, the translation of those faint pixels of light into the hard language of physics. And as the numbers came in, a sense of profound disbelief began to ripple through the astronomical community. This object was moving at 196,000 miles per hour. Let that number settle in your mind for a second. It translates to 54 miles for every single second that passes. To give this almost unimaginable velocity at terrestrial scale, picture a projectile traveling from New York City to Los Angeles, crossing the entire North American continent in just over 1 minute. That single staggering measurement told astronomers one clear, undeniable, and impossible thing. This visitor, this traveler, did not belong to us. It came from another star. Nothing born of our solar system, nothing gravitationally bound to our own sun, moves that fast. The asteroids and comets of our home system are sedate by comparison, cruising along their ancient elliptical paths at a leisurely 12 miles per second on average. This newcomer was a phantom, moving at nearly 5 times the speed of anything gravitationally tethered to our star. This extreme velocity was a testament to its incredible journey. It meant that this object had been traveling through the vast, cold, and silent emptiness between the stars for millions, perhaps even hundreds of millions of years. It was an ancient mariner of the void, a relic from a time and place we can only imagine, that had, by pure chance, stumbled into the gentle gravitational basin of our sun. In honor of its role as the first confirmed messenger from beyond, it was given a Hawaiian name, a word that perfectly encapsulates its significance, ʻOumuamua. The word means a scout, or a messenger arriving first from afar. It was a fitting tribute to a traveler that had journeyed through epochs. But its breathtaking speed was merely the opening chapter of its strangeness. As telescopes around the world, from the high deserts of Chile to the Canary Islands, turned their gaze upon this fleeting visitor, they discovered something else, something that made no sense at all. The object was tumbling, not spinning smoothly on an axis, but flipping end over end like a cosmic football thrown across the void. And as it tumbled, its brightness changed dramatically, dimming and flaring by a factor of 10 every 7.5 hours. This rhythmic fluctuation in light, this cosmic pulse, told us something astonishing about its shape, a shape unlike anything we had ever seen in space. The vast majority of asteroids are roughly round, shaped like cosmic potatoes, lumpy and cratered. Most comets are dirty snowballs, irregular but fundamentally compact shapes. This visitor was different. Radically, profoundly different. The dramatic changes in its brightness could only mean one thing. It was an object of extreme dimensions, at least 10 times longer than it was wide. The image that formed in the minds of astronomers was one of a celestial skyscraper lying on its side, a dark needle spinning silently through the vacuum of space. No known asteroid or comet within the confines of our solar system possesses such an extreme, elongated shape. The closest comparison one could draw was to a cosmic pencil, or perhaps, as some dared to whisper, an alien spaceship. Though that explanation seemed too fantastic, too far outside the realm of sober scientific consideration. And yet, there it was, an undeniable data point, a shard of dark rock or metal tumbling through our solar system, seemingly carved by forces or forged in an environment we could not begin to understand. As if its impossible speed and its unnatural shape were not strange enough, this visitor held one more surprise in store for us. A final, subtle anomaly in its motion that would puzzle and divide scientists for years to come. It would spark theories that ranged from the scientifically plausible to the absolutely extraordinary. The mystery of Oumuamua was only just beginning to unfold. And what happened next, as we tracked its journey away from our sun, would challenge the very foundations of what we thought we knew about the celestial mechanics of objects from other star systems. But compared to the profound enigma astronomers would discover hidden within its movement, the mystery of its shape was just the warm-up act. High upon the summit of Haleakala, the Panoramic Survey Telescope and Rapid Response System, PanSTARRS. It sits like a cosmic lighthouse, its vigilant eyes sweeping the dark Hawaiian skies for threats from the void. Every night, this fully automated hunter captures a colossal amount of data, creating deep images of the heavens. Its software meticulously searches for anything that moves against the unblinking background of distant stars. Most nights bring the usual celestial suspects into its field of view. There are the main belt asteroids plodding along their predictable, well-understood paths in the vast expanse between Mars and Jupiter. An occasional comet will wander in from the frigid outer darkness of the solar system, its path a long, graceful arc. Sometimes, a near-Earth asteroid will be flagged, an object requiring a closer look and more detailed calculations to ensure it poses no threat to our world. But the night of October 19th was different. The computer, in its silent, tireless analysis of the nightly data stream, flagged an object that made astronomers pause, put down their coffee, and stare intently at their screens. The discovery images showed what appeared to be a faint, unremarkable dot of light, moving steadily across the star field. At first, there was nothing particularly unusual about the movement itself. Space rocks move. That is their fundamental nature. But when the astronomers began the crucial work of calculating its trajectory, of plotting its path through our solar system, they realized they were looking at something that, according to all our experience, should not exist. This object was not orbiting our sun. It was not captured in the sun's immense gravitational embrace. It was merely passing through, a traveler on a cosmic highway, destined never to return. When you trace its path backward in time, plotting its inbound journey, it appears to have come from the direction of the brilliant star Vega in the constellation of Lyra. But here's where the story deepens into an abyss of time. The object took so long to reach us, a journey of approximately 300,000 years, that when its journey began, Vega was not even in that position in the sky. Our galaxy is not a static diorama. The stars themselves are in constant motion, orbiting the galactic center. This visitor had been wandering through the vast, cold emptiness of interstellar space since before modern humans walked the Earth. It had drifted through the cosmic void, while our distant ancestors were learning to fashion the first stone tools and paint their stories on cave walls. The Discovery team knew, with a certainty that must have been both exhilarating and humbling, that they had found something utterly unprecedented. For decades, astronomers had predicted that interstellar objects should exist. It was a logical necessity. Other star systems, with their own giant planets and chaotic early histories, must occasionally fling their own native asteroids and comets out into the galaxy, just as our own system does. Gravitational encounters, a celestial game of billiards played with planets and smaller bodies, can launch these objects at escape velocity, sending them on journeys that last for millions of years, drifting silently between the stars. The mathematics insisted that these lonely wanderers should be out there. But finding one was like looking for a single specific grain of sand on all the beaches of the Earth. And yet, finding it was only the beginning of the story. Once telescopes all over the world began to track this interstellar vagrant, the real, profound mysteries began to surface. The measurements of its reflected light, its color, told a story of a journey unlike anything in our direct experience. This object had been weathered, battered by high-energy cosmic radiation for hundreds of millions of years. High-energy particles, accelerated to near light speed by exploding stars and other violent cosmic events, had relentlessly bombarded its surface, slowly, patiently, changing its color to a deep, dark red, like ancient rust on a piece of cosmic metal. This dark reddish hue meant that this traveler was old, incredibly, unimaginably old. It had likely been wandering the space between the stars since long before our own solar system had settled into its current, stable configuration. While the young Earth was still being relentlessly bombarded by asteroids during the late heavy bombardment some 4 billion years ago, this object may have already been a seasoned traveler of the void, adrift in space, carrying the silent secrets of its long-lost home. Yet, even as astronomers celebrated the monumental discovery of the first confirmed interstellar visitor, they had no idea that the greatest mystery of all was still hidden, waiting to be discovered in the subtle nuances of its motion. Something about this object would soon defy every explanation they could imagine, pushing the boundaries of known physics. The astronomical community had never encountered anything quite like what the brightness measurements were telling them about this cosmic visitor. As the enigmatic object tumbled through the vacuum of space, a global network of telescopes meticulously tracked how its reflected light changed over time, moment by moment, hour by hour. You can picture a cosmic lighthouse beam spinning in the darkness, sweeping across the Earth. But instead of a steady, constant light, this distant beacon flickered. Its brightness fluctuated dramatically with a precise, repeating rhythm every few hours. The light we received from Oumuamua varied by more than 2.5 times as the object completed each rotation. To an astronomer, that much variation in brightness could mean only one thing. This was no ordinary, roughly spherical space rock. The vast majority of asteroids are shaped, more or less, like cosmic potatoes, with various bumps, craters, and irregularities, but fundamentally compact. Even the most elongated asteroids previously discovered within our own solar system rarely stretch to be more than 3 times longer than they are wide. But this interstellar wanderer was an outlier, a statistical anomaly of the highest order. The dramatic changes in its brightness suggested a body with an extreme aspect ratio, an object at least 10 times longer than its width. The mental image became inescapable. A skyscraper, perhaps the Empire State Building, lying on its side, tumbling end over end through the silent, cold vacuum of space. The shape was so extreme, so unlike anything formed by the slow, gentle accretion processes that build most asteroids, that some astronomers began to wonder if they were looking at a fragment. Perhaps this elongated shard was a piece of a much larger parent body, an object that had been catastrophically shattered by a violent cosmic collision millions or even billions of years ago, somewhere in another star system. Maybe 2 planetesimals, the building blocks of planets, had crashed together with unimaginable force, and this needle-like fragment was one of the pieces launched into interstellar space by the sheer violence of that ancient, distant impact. But other scientists, pushing the boundaries of conventional thinking, proposed an even stranger, more exotic possibility. What if this object was not made of rock at all? What if instead it was composed of ice, but an exotic form of ice that would be impossible to find near any star? In the profoundly cold depths of interstellar space, in the hearts of giant molecular clouds, conditions are so extreme that materials can exist in states we never encounter in our own solar system. Perhaps this visitor was made of solid hydrogen ice, formed in the crushing pressures and near absolute zero temperatures of a cosmic nursery between the stars. The hydrogen ice theory was compelling because it could potentially explain the bizarre shape. As this interstellar iceberg made its journey inward, approaching the warmth of our sun, its outer layers would begin to sublimate away, turning directly from solid to gas. This process would not be uniform. It would act like a celestial sculptor's tool, carving the object into increasingly strange and elongated configurations. Like a cosmic sculpture being shaped by starlight, the warming ice would reshape itself as it traveled deeper and deeper into our solar system. This slow, steady erosion could plausibly transform a more conventional, round object into the extreme needle shape that so puzzled astronomers. Yet even this elegant and exotic explanation faced significant problems. The object appeared to be too small and, crucially, too dark to be made entirely of ice. Its surface reflected sunlight in a way that was more consistent with rock or metal, not the bright, shiny surface one would expect from a body made of ice. And its deep red color suggested a surface that had been weathered and chemically altered by cosmic radiation for millions of years, a process that should have destroyed any surface ice. This led some researchers to propose the most radical, most paradigm-shifting explanation of all. What if this was not a natural object? The profoundly unusual shape was unlike any asteroid or comet ever observed in nature. The precise, elongated form looked, to some, almost as if it had been engineered. Could this be a piece of debris from an alien civilization? Perhaps a fragment of advanced technology from another star system, a probe or a ship component designed for purposes we could not possibly imagine. While the vast majority of scientists remain deeply skeptical of the alien hypothesis, preferring to exhaust all possible natural explanations first, they could not deny that this object challenged every single assumption they held about what constitutes a natural space rock. The shape, however, was only the beginning of the mystery. The velocity measurements, when analyzed with extreme precision, told a story that made astronomers question everything they thought they understood about the fundamental forces governing the motion of objects in space. This interstellar visitor wasn't just moving fast. It was moving at a speed that was almost impossible to reconcile with its apparent nature. At 196,000 miles per hour, it was traveling nearly 5 times faster than the typical comets and asteroids that populate our solar system. To truly understand how extraordinary this speed was, imagine standing next to a highway where the normal flow of traffic moves at a steady 60 miles per hour. Suddenly, a vehicle rockets past you at 300 miles per hour. The sheer difference in velocity would be jarring. Almost unbelievable. That's the cosmic equivalent of what astronomers were witnessing with Oumuamua. The speed alone was the ironclad proof that this object came from interstellar space. Nothing gravitationally bound to our sun, no object native to our solar system, could ever achieve such a velocity through natural gravitational interactions within our system. Even our fastest spacecraft, like the Parker Solar Probe or the Voyager probes, which have been boosted by multiple planetary flybys in a gravitational slingshot maneuver, barely reach speeds of 40 miles per second. This cosmic wanderer was cruising at over 50 miles per second, carrying the immense kinetic energy of its million-year journey between the stars. But such incredible speed creates its own set of mysteries in the near vacuum of space. When an object moves this fast relative to our solar system, it experiences subtle effects that slower-moving objects never encounter. The interstellar medium, the incredibly thin but ever-present gas and dust that fills the space between the stars, becomes like a cosmic headwind. Over the course of millions of years, this constant, gentle resistance should act as a brake, slowing down any object traveling through it. Yet, this visitor had maintained its incredible velocity, which suggested to some that it had not been wandering for as long as its trajectory initially implied, adding another layer of complexity to its history. The analysis of its trajectory revealed yet another puzzle. When astronomers traced its path backward to its point of origin, they found that this object had not been traveling in a perfectly straight line through the galaxy. Something, at some point during its long journey between the stars, had influenced its course. Perhaps it had passed close to another star system along the way, where the gravitational forces of an unseen star and its planets had bent its path. Or maybe it had traversed one of the massive, dark clouds of gas and dust that drift silently through our galaxy, each containing enough raw material to build thousands of new star systems. The speed also meant that observers had only an incredibly limited window of time to study this cosmic messenger. Unlike the asteroids and comets that orbit our sun for months, years, or even millennia, this interstellar visitor was just passing through. It had already made its closest approach to the sun by the time astronomers had even discovered it. By the time the world's telescopes could be trained on it, it was already racing away from us at tremendous velocity, growing fainter and more difficult to observe with each passing day. Telescopes around the world, from the largest professional observatories to dedicated amateur networks, raced against time. The goal was to gather as much data as humanly and technologically possible before the object disappeared forever back into the unimaginable depths of interstellar space. Every single night of observation was precious. Every measurement, no matter how small, might reveal the crucial clues needed to understand the nature of this visitor and the distant star system that had sent it on its cosmic journey. The intense pressure to understand this object quickly led to an international collaboration of a scale and speed rarely seen before in astronomy. Observatories from Hawaii to Chile, from Arizona to South Africa, pointed their powerful instruments at this one fleeting, faint target. Radio telescopes, like the Green Bank Observatory, listened intently for any signals, any hint of artificial origin, however faint. Infrared detectors like the Spitzer Space Telescope searched for heat signatures that could reveal the object's composition and temperature. Yet even as this unprecedented observational campaign was gathering terabytes of precious data, the object had one final, profound surprise waiting for the scientific community. It was a subtle anomaly in its motion, a ghost in the machine of celestial mechanics, something that would challenge the very laws of physics as we apply them to small bodies moving through space. In June of 2018, nearly 8 months after the initial discovery, a team led by Marco Micheli at the European Space Agency announced a finding that would send shockwaves through the entire astronomical community. This interstellar visitor, Oumuamua, was not following the precise path that the laws of gravity predicted for it. As telescopes continued to track its movement away from the sun, they found it was deviating, ever so slightly, from the trajectory that should have been dictated solely by the gravitational forces of the sun, the planets, and other bodies in the solar system. It was accelerating, not dramatically, not with the force of a rocket engine, but measurably and consistently. The deviation was tiny, a whisper of a push. Imagine a perfectly smooth, miles-long table and a marble rolling across it. Suddenly, that marble gains an extra tiny push from an invisible, ethereal hand. The force causing the acceleration was incredibly small, about the same amount of pressure you would feel if someone gently blew on your face. But for a massive cosmic object traveling at tremendous speed through the frictionless vacuum of space, this represented a significant and profound anomaly. In space, where there is no air resistance, no friction, objects are supposed to follow predictable paths determined by gravity alone. Planets, asteroids, comets, they all meticulously obey these fundamental, ironclad laws of celestial mechanics. This visitor, it seemed, was apparently writing its own rules. For astronomers, this presented a deep and fascinating puzzle. The acceleration was in the right direction, away from the Sun, and it had the right characteristics to be caused by a well-known cometary phenomenon, outgassing. When comets, which are essentially dirty snowballs, approach the Sun, the ice on their surface doesn't melt. It turns directly into gas in a process called sublimation. This escaping gas, venting from the comet's surface, acts like a natural, low-thrust rocket engine, giving the comet a small but measurable push away from the Sun. This phenomenon is perfectly well understood and has been observed and measured in thousands of comets throughout history. But Oumuamua showed absolutely no visible signs of the outgassing that is supposed to create this kind of acceleration. There was no visible coma, the bright, fuzzy cloud of gas and dust that envelops an active comet. There was no tail, streaming away from the object as gas and dust particles are pushed by the solar wind and radiation pressure. The world's most powerful telescopes saw only a dark, apparently solid, point-like object, tumbling silently through space. And yet, somehow, it was accelerating, as if it were a typical active comet. The mystery deepened even further when astronomers calculated just how much outgassing would be required to produce the observed acceleration. For a normal comet, the sheer amount of material that would need to be ejected from its surface would create easily visible signs of activity. The object would be shrouded in a bright coma spanning thousands of miles. It would sport a magnificent tail, potentially visible to amateur astronomers with small backyard telescopes. Instead, even the most sensitive instruments, like the Hubble and Spitzer space telescopes, detected no trace whatsoever of such activity. This stark contradiction led to a cascade of increasingly exotic and creative explanations. Perhaps the object was ejecting material that was simply too dark to see, like fine particles of pure carbon that would absorb light rather than reflect it. Maybe it was venting gas in narrow, tightly focused jets that just happened to be pointed directly away from Earth, making the outgassing invisible from our particular vantage point. Some scientists proposed that the acceleration wasn't from outgassing at all, but from the pressure of sunlight itself. The solar radiation pressure theory suggested that the gentle but relentless force of photons streaming from the Sun was pushing the object. However, this explanation required the visitor to be extremely lightweight, to have the density of foam or styrofoam, or to be shaped like an incredibly thin, expansive solar sail. Sunlight does carry momentum, and when it reflects off a surface, it can provide a tiny push. For most celestial objects, this radiation pressure is utterly negligible compared to the overwhelming force of gravity. But for an object with a very specific and unusual combination of size, shape, and density, sunlight could, in theory, provide a measurable acceleration. This explanation, born from the lack of any other, led directly to the most controversial and widely publicized theory of all about the nature of this cosmic wanderer. It was a proposal that would divide the scientific community, capture the public imagination worldwide, and force us to confront the profound question of our own uniqueness in the cosmos. Every spectacular comet that has ever graced our night sky from Halley's Comet to Hale-Bopp, follows the same basic, beautiful script, a story written by the fundamental laws of physics and chemistry. As a comet makes its long journey from the cold, dark outer reaches of the solar system, the faint warmth of the distant sun begins to work its magic. Most comets are, in essence, dirty snowballs, primordial mixtures of various ices, like water, carbon dioxide, and methane, intermixed with rock and dust. They are relics that have remained deep frozen for billions of years in the frigid depths beyond the orbit of Neptune, in regions known as the Kuiper Belt and the Oort cloud. When sunlight, even the weak sunlight of the outer solar system, first hits this ancient, pristine ice, something beautiful and transformative happens. The ice does not melt into a liquid, as it would on Earth. Instead, in the vacuum of space, it sublimates, transforming directly from a solid state into a gaseous one. This escaping gas doesn't leave alone. It carries fine dust particles with it, creating the glowing ethereal atmosphere around the comet's nucleus that we call the coma. The coma can grow to be truly immense, sometimes larger than the planet Jupiter, spanning hundreds of thousands of miles of space, all emanating from a nucleus that might only be a few miles across. The solar wind, a constant stream of charged particles flowing outward from the sun, then pushes this cloud of gas and dust away from the comet, creating the magnificent, iconic tail that can stretch for millions of miles across the sky. The tail, or rather tails, as comets often have two, a bluish ion tail and a whitish dust tail, always points away from the sun, like cosmic hair blown by a stellar wind. This interaction creates the breathtaking sight of comets that seem to race across the sky, with their brilliant, flowing streamers trailing behind them. The entire process is so well understood, so predictable, that astronomers can forecast with great accuracy when a comet will develop its tail, and how bright it is likely to become as it makes its closest approach to the sun. But this interstellar visitor, Oumuamua, followed none of these established rules. Despite exhibiting the subtle acceleration signature that is typical of a comet shedding material, it displayed absolutely no visible signs of this activity. The most powerful and sensitive telescopes on Earth and in space detected no coma, no fuzzy halo around the object. There was no tail streaming away from it. No fine dust particles were seen reflecting sunlight to create the characteristic glow of an active comet. This profound absence of evidence was not for lack of trying. Astronomers employed every single technique available in their considerable toolkit to search for the faintest signs of outgassing. They used spectrographs to look for the chemical fingerprints, the spectral signatures, of common comet gases like water vapor, carbon monoxide, and carbon dioxide. They meticulously searched for the scattered sunlight that would be reflected from a cloud of even microscopic dust particles. They monitored the object with powerful infrared telescopes that could detect the faint heat signatures emitted by sublimating ice and the warm dust it would release. The result was always the same: nothing. The Spitzer Space Telescope, one of the most sensitive infrared observatories ever built by humanity, stared intently at this cosmic wanderer for hours, accumulating faint infrared light. If the object were shedding material like a normal comet, Spitzer would have undoubtedly detected the warm dust particles glowing in infrared light. Instead, the telescope saw only the object itself, a dark and apparently inert point source against the cold background of space. This led the scientific community to a crucial, unavoidable realization. If Oumuamua was indeed accelerating without any visible outgassing, then either it was shedding material in a way that was completely unlike any known comet, or the acceleration had a different, more exotic cause entirely. Some scientists clung to the possibility of invisible outgassing, proposing that the object might be venting gas through deep cracks or isolated vents that just happened to be pointed away from Earth, making the activity invisible from our perspective. Others suggested that the ejected material might be composed of particles that were too dark to detect, like pure carbon soot that would absorb light rather than reflect it. But the most radical explanation, the one that captured headlines, suggested that this visitor was not a comet at all. Instead, it might be something far stranger, an object whose acceleration came not from the rocket effect of sublimating ice, but from the gentle, persistent pressure of sunlight itself. This theory, championed by a respected Harvard professor, would soon thrust him into the center of a swirling scientific controversy that continues to this day. A debate that forces us to question the limits of natural explanation and the possibility of the extraordinary. The astronomical community found itself grappling with a puzzle that seemed to violate everything it understood about the behavior of small bodies in space. The contradiction was stark and unavoidable. Oumuamua was accelerating like a comet, but it looked like an asteroid. This cognitive dissonance sent theoretical astrophysicists scrambling through physics textbooks, complex scientific papers, and powerful computer models, searching for any plausible natural phenomenon that could account for all the bizarre observations. A team of researchers, including Alan Jackson and Stephen Desch at Arizona State University, proposed an elegant and intriguing solution. The visitor might be a fragment of nitrogen ice, chipped off a Pluto-like world in another, distant star system. In this carefully constructed scenario, an impact on an exo-Pluto could have ejected a shard of its frozen nitrogen surface into interstellar space. As this nitrogen iceberg approached our Sun, the solid nitrogen would begin to sublimate, vaporizing from the surface. This outgassing of nitrogen gas would provide the gentle, non-gravitational thrust that was observed, while being almost completely invisible to our telescopes. Nitrogen gas does not glow brightly or reflect sunlight efficiently in space, meaning it could create the acceleration without producing a visible coma or tail. The nitrogen ice theory was particularly attractive because it solved several problems at once. It elegantly explained the acceleration without requiring visible outgassing. It also accounted for the strange elongated shape, suggesting it could be the result of uneven sublimation, with the sun's warmth carving away at the nitrogen ice, leaving behind a progressively thinner, more cigar-like remnant. It even provided a plausible and natural origin story, since nitrogen ice is known to be common on the surfaces of dwarf planets like Pluto and other similar objects that likely exist in abundance around other stars. Other researchers pursued different, equally creative lines of inquiry. Some proposed that the object was made of solid hydrogen ice, a material that could theoretically form in the extremely cold and dense conditions of interstellar molecular clouds, the birthplaces of stars. As this hypothetical hydrogen iceberg neared the Sun, it would sublimate with incredible rapidity, providing a powerful accelerative force while remaining essentially invisible to our instruments. The resulting hydrogen gas would be far too thin and dispersed to create a detectable coma or tail. A team led by Yun Zhang suggested another possibility, that the visitor might be a fractal aggregate, a very fluffy, porous structure made of loosely bound dust and ice particles, like a cosmic dust bunny. Such an object could have an extremely low density, making it unusually susceptible to the effects of solar radiation pressure. In this model, the gentle but constant pressure of photons from the Sun hitting the object's large surface area could provide the observed acceleration without requiring any outgassing at all. Meanwhile, Avi Loeb, a distinguished professor at Harvard University, was meticulously developing the most controversial and thought-provoking explanation of them all. Working with his postdoctoral researcher Shmuel Bialy, Loeb performed detailed calculations and concluded that the observed acceleration pattern was perfectly consistent with an artificial light sail, a very thin, reflective membrane designed to catch sunlight for propulsion. Such technology has long been proposed for our own future interstellar space missions, and Loeb argued that an advanced alien civilization might use similar, highly efficient technology for their own interstellar travel. The light sail hypothesis suggested that Oumuamua might be a piece of alien technology, either a functioning probe deliberately sent to investigate our solar system, or perhaps derelict debris from some long-ago cosmic accident involving extraterrestrial engineering. While Professor Loeb readily acknowledged that natural explanations were statistically more likely, he passionately argued that the scientific method requires us to consider all possibilities that fit the available data, no matter how extraordinary or uncomfortable they may seem. The vigorous debate that followed this proposal would reveal deep divisions within the scientific community, not just about Oumuamua itself, but about the very nature of scientific inquiry, the burden of proof for extraordinary claims, and how to handle anomalous observations that don't fit neatly into our existing paradigms. Yet even as theorists battled over these competing and fascinating explanations, a new discovery, a new insight, was on the horizon. It would provide what is now considered the most compelling and widely accepted solution to the mystery. In March of 2023, Jennifer Bergner, a researcher at the University of California, Berkeley, announced a breakthrough that would transform our understanding of this enigmatic cosmic wanderer. Working in collaboration with Daryl Seligman at Cornell University, Jennifer Bergner had been deeply studying a question that was key to the Oumuamua puzzle. What actually happens to ordinary ice when it travels through the hostile environment of interstellar space for millions upon millions of years? The crucial insight, the flash of understanding, came from a deep dive into the physics of how relentless cosmic radiation affects common water ice during these incredibly long and lonely journeys. High-energy particles, known as cosmic rays, which are born in the cataclysm of exploding stars and other violent cosmic events, constantly bombard any object that drifts through the space between star systems. When these energetic cosmic rays strike a body made of water ice, they act like microscopic bullets, breaking apart the H2O molecules in a process similar to what happens inside a particle accelerator on Earth. These energetic impacts have enough force to split the water molecules into their constituent atoms, hydrogen and oxygen. But in the extreme cold and vacuum of deep space, these fragments cannot escape immediately. Instead, something remarkable happens. The hydrogen gas becomes trapped within the remaining crystalline structure of the ice, like microscopic gas bubbles frozen inside a solid block of ice. Bergner and Seligman realized that this process could continue uninterrupted for millions of years as an object drifts through the interstellar medium. Over such vast, almost unimaginable timescales, the constant bombardment of cosmic radiation could convert a significant fraction, perhaps up to 30%, of the object's water ice into trapped, pressurized molecular hydrogen gas. The object would essentially become a hydrogen battery, storing up kinetic energy from cosmic rays for millions of years, waiting patiently for something to trigger its release. That trigger, they proposed, would be the warmth of an approaching star. As an interstellar wanderer like Oumuamua entered our solar system and began to heat up, even slightly, the ice structure itself would start to change. The warming would cause the ice to anneal, to reorganize itself into a more stable crystalline form. This structural shift would collapse the tiny, microscopic pockets where the hydrogen gas had been trapped for eons. Like squeezing a sponge filled with gas, this process would release the stored hydrogen out into space. The gently escaping hydrogen would act as a perfect, invisible, natural rocket engine, providing the precise, low-level acceleration that had so profoundly puzzled astronomers. And crucially, hydrogen gas is essentially invisible to most astronomical instruments. Unlike the dust and heavier gases like carbon dioxide that create the bright, visible tails of comets, hydrogen produces almost no detectable signature when it escapes into the vacuum of space. The object would accelerate exactly like a comet, while appearing completely inert and inactive to our most powerful telescopes. This single, elegant theory explains several of the key mysteries of Oumuamua all at once. It perfectly accounted for the non-gravitational acceleration without requiring any visible outgassing. It provided a completely natural mechanism that would work on any water-rich object, like a typical comet, that had spent millions of years marinating in the cosmic radiation of interstellar space. It even helped explain why the acceleration was so gentle compared to that of typical comets, since the lightweight hydrogen molecules carry less momentum than the heavier molecules like water and carbon dioxide that are usually ejected by sublimating ice. The trapped hydrogen outgassing theory also fit perfectly with what astronomers knew about the likely origin of Oumuamua. If it had formed as a normal, water-rich comet around another star and was then ejected into interstellar space by a gravitational interaction, cosmic radiation would have had more than enough time, millions of years, to create the internal hydrogen reservoirs needed to power the observed acceleration. The theory required no exotic, undiscovered materials or alien technology, just the predictable, well-understood effects of cosmic radiation acting on ordinary water ice over immense cosmic timescales. Detailed computer models showed that the proposed mechanism could easily account for both the magnitude and the direction of the observed acceleration. The release of the trapped hydrogen would naturally be driven by the side of the object facing the Sun, creating thrust in exactly the direction, away from the Sun, that was observed by astronomers. However, even this brilliant and compelling theory, which solved the central mystery of the acceleration, still could not fully explain one crucial aspect of this cosmic visitor: its bizarre, extreme, needle-like shape, which remained in a profound and unsettling anomaly. The discovery of the first interstellar visitor, and the frantic, brief scramble to study it, revealed a sobering truth that scientists and engineers at NASA had suspected for decades. We were effectively blind to small, fast-moving objects approaching Earth from the depths of space. While our existing sky surveys, like the magnificent Pan-STARRS telescope, excelled at finding large, potentially civilization-ending asteroids months or even years before a potential impact, they were designed and optimized to detect these big threats from very far away. But what about the smaller objects, perhaps only a few hundred feet across, that could appear suddenly in our cosmic backyard with just days or weeks of warning? The Chelyabinsk meteor of 2013 had already served as a stark and powerful demonstration of this very vulnerability. An object estimated to be about 60 feet in diameter entered the atmosphere and exploded over Russia with the force of approximately 30 Hiroshima bombs. The resulting shockwave injured over 1,000 people and caused damage to thousands of buildings across a wide area. Despite all of our sophisticated sky surveys, this dangerous cosmic projectile arrived completely and utterly undetected. The reason was simple. It had approached Earth from the direction of the Sun, a celestial blind spot where the overwhelming glare of our own star makes it impossible for ground-based telescopes to look. Dr. Larry Deneau and his dedicated team at the University of Hawaii realized that truly defending the Earth from this type of threat required a fundamentally different approach. Instead of peering deep into space to look for large objects far away, they needed to build a system that could scan the entire visible sky every single night, from horizon to horizon. This new system would be optimized specifically for finding the smaller, closer threats that might appear suddenly, giving humanity the crucial days or weeks of warning needed to prepare, evacuate, or potentially respond. Thus, from this urgent need was born the Asteroid Terrestrial-impact Last Alert System, or ATLAS. The name itself perfectly captures the system's core mission. This would be our final line of defense, our last alert system, the final warning bell for objects that are too small, too close, or approaching from the wrong direction for other, larger surveys to detect in time. ATLAS was specifically designed to be able to spot a 60-foot Chelyabinsk-sized asteroid several days before a potential impact, and a larger, 300-foot city-threatening asteroid several weeks before impact. The engineering challenge to create such a system was immense. To scan the entire sky every night required telescopes with enormous fields of view and cameras with extreme sensitivity. Each individual ATLAS telescope would need to be able to capture an area of the sky more than 100 times larger than the full moon in a single exposure. The cameras themselves would need to be sensitive enough to detect objects so faint that they are invisible to the naked eye by a factor of 100,000. NASA, recognizing the critical importance of this new capability for planetary defense, funded the project with an initial $5 million in 2013. The first two telescopes were constructed in Hawaii, strategically positioned on the volcanic peaks of Haleakala and Mauna Loa, about 100 miles apart. This separation provided crucial redundancy against localized bad weather and also allowed for parallax measurements, which could be used to quickly and accurately determine the distance to any newly discovered objects. By 2017, the very same year that Oumuamua was discovered, both of the Hawaiian ATLAS telescopes were fully operational and were diligently scanning the northern sky every clear night. The completely automated system captured over 250 gigabytes of data every single night, with powerful computers analyzing every image in real time to identify any moving objects against the starry background. The system was capable of processing the informational equivalent of the entire text of Wikipedia every single night, relentlessly searching for the faint, telltale trails of cosmic wanderers. But the two Hawaiian telescopes could only see the northern half of the celestial sphere, leaving the southern hemisphere largely unmonitored. Recognizing this critical limitation, NASA provided funding for two additional, identical telescopes to be built in the southern hemisphere. These new, vigilant eyes would soon join the network, completing a global shield, and they would ultimately make a discovery that would dwarf even the profound mystery of the first interstellar visitor. By the early months of 2022, humanity had achieved something truly unprecedented in our long history of watching the cosmos. 4 identical, robotic telescopes separated by thousands of miles across the globe began working in perfect concert as a single, unified planetary defense system. The 2 original ATLAS stations in Hawaii were now joined by new, state-of-the-art installations in South Africa, at the Sutherland Observing Station, and in Chile, at the ELSAS Observatory. This strategic placement created the first sky survey in history capable of monitoring the entire dark sky every 24 hours. Each individual telescope in this remarkable global network represents a marvel of modern astronomical engineering. The optics are designed to capture light with mirrors that are only 20 inches across, which is actually smaller than many high-end amateur telescopes. But what these telescopes lack in sheer mirror size, they more than make up for in their incredible field of view. Each telescope can image a vast area of the sky measuring 7.4 degrees across, which is equivalent to lining up 15 full moons side by side. This enormous field of view is what allows each station to photograph approximately 1/4 of the entire visible sky in a single night's work. The custom-built cameras attached to these telescopes are technological wonders in their own right, containing 110 million pixels, allowing them to capture immense detail across these vast swaths of space with every single exposure. To put this into a more tangible perspective, if you were to print out a single atlas image at a normal photograph resolution, it would be large enough to cover an entire professional basketball court. Every night, the 4 telescopes together capture enough raw data to fill the memory of more than 50 high-end smartphones. The global positioning of these robotic sentinels is the key to their effectiveness, creating overlapping coverage that ensures no blind spots remain in our watch. When it is daytime in Hawaii and the telescopes there are dormant, the telescopes in South Africa and Chile are in the deep darkness of their night, continuing the vigilant watch. When storms, clouds, or even volcanic eruptions affect one of the sites, the others maintain the constant surveillance. The carefully planned 120-degree spacing between the sites means that small, fast-moving asteroids, which might only be visible from Earth for a day or two before passing by or impacting, cannot slip through the net undetected. Each telescope follows the same precise, automated routine every clear night. The master control system divides the visible sky into approximately 1/500 separate patches, like a vast cosmic checkerboard. The telescope then takes 4 separate 30-second exposures of each patch, with these exposures separated by about 10 minutes. This clever 4-shot strategy allows the powerful computer systems to easily identify anything that is moved between the images and to distinguish real, moving asteroids from instrumental artifacts like cosmic ray hits, passing satellites, and the faint light of distant quasars. The data processing for this immense fire hose of information happens in real time, right at each observatory site. Powerful computer clusters analyze every image immediately after it is captured, identifying any moving objects and calculating their preliminary orbits on the spot. The system then automatically compares each new discovery against vast, comprehensive databases of all known asteroids and comets, flagging only the genuinely new and unknown objects for the attention of human astronomers. Within hours of a discovery, any confirmed new objects are automatically reported to the Minor Planet Center, the official international clearinghouse for all asteroid and comet discoveries. This highly efficient, automated detection system has completely revolutionized our ability to find and track cosmic threats. Since becoming fully operational, the Global Atlas Network has discovered over 700 near-Earth asteroids and 66 comets. Crucially, the system has successfully detected 2 very small asteroids that actually went on to impact the Earth, providing essential, real-world validation of its ability to spot incoming threats with actionable warning times. But the capabilities of Atlas extend far beyond just planetary defense. As a natural byproduct of scanning the entire sky multiple times each night, the system has become one of the most productive surveys in the world for finding other transient cosmic phenomena, such as exploding stars known as supernovae, variable stars, and other distant, exotic events. And in the quiet early days of July 2025, this powerful global network would make a discovery that would once again reshape our entire understanding of the nature of visitors from other star systems. The night of July 1, 2025, began like any other night at the Atlas station, perched high in the dry, clear air of the Chilean Andes. The robotic telescope at the El Sos Observatory whirred to life, its dome silently opening to the pristine southern sky as the last light of the sun set behind the distant mountains. The automated systems powered up the sensitive 110-megapixel camera and began the nightly, systematic ritual of capturing the cosmos, one vast patch of sky at a time. The powerful computer algorithms housed in a climate-controlled server room began their tireless work, processing each image within minutes of its creation, relentlessly searching for the telltale signature of motion that betrays the presence of asteroids and comets moving against the static stellar background. At first, the discovery that evening appeared to be entirely routine. The detection software flagged a very faint object, moving slowly across the starfield. This was typical of the distant main belt asteroids that Atlas finds on a regular basis. The preliminary calculations performed by the system suggested it was just an unremarkable space rock, following a normal, predictable orbit around the Sun. The automated systems dutifully logged the new discovery, assigned it a temporary designation, and prepared to move on to the next patch of sky in its nightly survey. But as additional images of this object were automatically accumulated throughout the night, as more data points were added to its trajectory, something extraordinary, something impossible, began to emerge from the data. The object was not following the gentle, closed elliptical path that is typical of all solar system objects. Instead, its trajectory showed the unmistakable, distinctive signature of a hyperbolic orbit. It was the exact same type of open-ended path that had been followed by the mysterious first interstellar visitor, Oumuamua, years earlier. This new object was simply moving too fast to be gravitationally bound by the Sun. The confirmation of its interstellar origin triggered immediate, high-priority alerts that were sent out to astronomers and observatories all around the world. Within a matter of hours, powerful telescopes in multiple countries interrupted their scheduled observations and swung their massive structures toward the object's position in the sky, racing to gather as much data as possible before it, too, could disappear back into the depths of space. The Gemini North Telescope in Hawaii, the Canada-France-Hawaii Telescope on Mauna Kea, and the Lowell Discovery Telescope in Arizona all joined the urgent observational campaign. But unlike the first interstellar visitor, which remained a mysterious, point-like source of light, this new object revealed its true nature almost immediately. Central core. The characteristic signature of a cometary coma was unmistakable. This was not a dark, inert, mysterious rock like the first visitor. This was an active comet, complete with the glowing, ethereal cloud of gas and dust that makes comets such a beautiful and visible spectacle in our solar system. The clear presence of a coma meant that this interstellar wanderer was actively shedding material as it approached the Sun, behaving just as normal, well-understood comets do. Ice on its surface was sublimating into the vacuum of space, creating the beautiful display that has captivated and mystified humans throughout our history. But this comet was special. It carried within its icy nucleus the chemical signatures of another star system, offering an unprecedented, direct opportunity to study the composition of the raw materials that formed around a distant, alien star. The veteran comet hunters David Jewett and Jane Liu quickly confirmed the object's activity using the Nordic Optical Telescope. Their crucial observations showed that the coma was clearly visible and was steadily growing as the object moved closer to the Sun. For the very first time in history, astronomers were watching an active, living comet from another star system perform the exact same cosmic dance, following the same physical rules that our own native comets have followed for billions of years. The discovery sent waves of pure excitement and anticipation through the entire astronomical community. Unlike the enigmatic and puzzling first visitor, this new object promised to reveal its secrets through well-understood, familiar processes. Spectroscopic analysis of its light could determine the precise chemical composition of its nucleus and its coma. A sequence of images over time could track how its activity evolved, as it was subjected to the increasing heat of our sun. But this profound excitement was tempered with a sense of urgency, as this cosmic messenger, this sample from another world, would not linger for long in our cosmic neighborhood. The official announcement of the discovery came on July 2, 2025, sending ripples of intense excitement through observatories, universities, and space agencies worldwide. The Minor Planet Center, the internationally recognized authority for tracking and cataloging asteroids and comets, issued the formal designation that would make history. The object, initially cataloged as C-2025N1 Atlas, was then given the official interstellar designation it deserved, 3I. The I for interstellar, and the 3 signifying that this was the third confirmed interstellar object ever discovered by humanity. The first, of course, had been the mysterious elongated visitor Oumuamua in 2017. The second was the comet 2I/Borisov, discovered in 2019, which behaved much like a normal comet but also arrived on a hyperbolic trajectory from interstellar space. This new discovery, 3I, represented something completely unprecedented. For the very first time, astronomers had detected an active interstellar comet while it was still on its inbound journey, approaching the Sun, not after it had already rounded our star and begun its long departure from our solar system. This crucial timing advantage was a game-changer. It meant that observers would have many months to study the object, as its activity steadily increased, rather than the desperate, frantic race against time that had characterized the observations of the previous 2 interstellar visitors. Immediately following the announcement, astronomers around the world began digging through their archival data. So-called pre-discovery observations quickly emerged from the archives of various telescope surveys. The powerful Vera Rubin Observatory, still in its science validation phase, had actually imaged the object during its early test observations starting on June 21st, though the images had not been fully processed and analyzed until after the official Atlas discovery. Even more remarkably, NASA's Transiting Exoplanet Survey Satellite, or TESS, a space telescope designed to find planets around other stars, had captured the comet even earlier. Its observations extended all the way back to May 7th, when the object was still over 6 times farther from the Sun than the Earth is. These incredible archived observations revealed that the interstellar comet had been active for much longer than anyone had expected. Even at these enormous distances from the Sun, where water ice should remain frozen solid, the object was already showing clear signs of sublimation and outgassing. This crucial detail suggested that its activity was being powered by more volatile materials than water, possibly frozen carbon monoxide or carbon dioxide, which can turn into gas at much lower, much colder temperatures. The detailed trajectory analysis, now based on months of observational data, confirmed what astronomers had suspected from the very first observations. When its path was traced backward through time, the comet's journey clearly originated from far beyond the gravitational influence of our solar system. It had approached our system from the direction of the constellation Sagittarius, the same direction as the dense, star-rich central bulge of our own Milky Way galaxy. The object had been traveling for millions of years before it finally, by pure chance, encountered our Sun's gravitational influence. And unlike the first mysterious visitor, Oumuamua, this new interstellar comet posed no puzzles whatsoever about its acceleration. This steadily growing coma and the emerging faint tail explained its motion perfectly through the well-understood physics of cometary outgassing. As ice sublimated from its nucleus, the escaping gas provided a gentle, natural rocket effect that was subtly altering the comet's trajectory. There was no need to invoke exotic, invisible materials or controversial theories about alien technology. This discovery was also a powerful vindication of the design philosophy behind the Global Atlas Network. By diligently scanning the entire sky every single night, the system had successfully detected this visitor while it was still far enough from the Sun to allow for an extensive, months-long campaign of detailed observations. Earlier detection systems, which were primarily focused on finding very large threats months or years in advance, would have likely missed this smaller, fainter object as it approached from the southern sky. Within days of the announcement, the Hubble Space Telescope, humanity's premier eye on the cosmos, had been redirected to acquire its first images of the interstellar visitor. These breathtaking observations would begin the process of unlocking the ancient secrets that had been traveling, locked in ice between the stars for millions of years. The first detailed images transmitted back to Earth from the Hubble Space Telescope revealed a sight that had never before been captured in the entire history of humanity. Here, in stunning clarity, was an active comet from another star system, and it was displaying the same beautiful ethereal phenomena that have inspired awe and wonder in skywatchers for millennia. The coma. The glowing atmosphere of the comet stretched for over 8,000 miles across, a vast, luminous cloud of gas and dust that made the tiny, unseen nucleus visible across the immense distances of space. The powerful spectrographs attached to Hubble began their work of dissecting the comet's light, revealing the familiar chemical fingerprints of water vapor, carbon monoxide, and carbon dioxide. These were the very same materials that power the activity of comets that were born in our own solar system. But nestled within this familiar chemistry, this cosmic visitor carried subtle, crucial differences that revealed its alien origin. The dust particles that had been lifted from the nucleus and were now suspended in its coma were, on average, larger than the dust particles typically found in our own solar system's comets. Precise measurements showed that the small dust grains, about 1 micrometer in radius, were being ejected from the nucleus at speeds of around 72 feet per second. The larger grains, 100 times bigger, were moving much more slowly, at about 6.5 feet per second. These specific dust properties told a fascinating story of formation in a different stellar environment. This comet had likely formed in the cold, outer regions of another planetary system, a place where different temperatures and different chemical conditions had created primordial ice mixtures unlike those found in our solar system's own comet reservoirs, the Kuiper Belt and the Oort cloud. The presence of larger dust grains suggested that the parent star system may have had a higher abundance of heavy elements available during the chaotic period of planet and comet formation. As the month of July progressed into August, telescopes around the world tracked the steady, predictable growth of the coma as the interstellar visitor continued its silent, inexorable approach toward the Sun. The Canada-France-Hawaii telescope captured a series of deep images showing the emergence of a faint, nascent tail. It was the classic elongated feature that always points away from the Sun as the solar wind pushes the comet's thin atmosphere out into space. For the very first time, astronomers were witnessing, in real time, an interstellar comet develop its full, glorious regalia of activity. The tail itself was a treasure trove of information, carrying important clues about the comet's composition and the specific conditions of the solar wind it was encountering on its journey. Unlike the invisible hydrogen gas that might have powered the mysterious acceleration of Oumuamua, this comet's tail contained easily detectable dust and gas that revealed their chemical makeup through the science of spectroscopy. Each element and molecule present in the tail left its own unique, indelible fingerprint in the light that was reflected and emitted, allowing for a detailed chemical inventory. Ground-based telescopes around the world joined the massive observation campaign, creating an unprecedented international effort to study this messenger from the stars. The Gran Telescopio Canarias, currently the largest single-aperture optical telescope in the world, was able to determine that the comet's solid nucleus was rotating once every 16 3/4 hours. This rotation rate was quite typical for small comets, suggesting that despite its incredible interstellar journey, the object had retained the basic physical properties of the environment in which it was born. The European Southern Observatory's Very Large Telescope contributed a series of observations that tracked how the comet's overall brightness varied as different, potentially more or less active, parts of its nucleus rotated into direct sunlight. These brightness variations were seen to decrease over time, an indication that the nucleus was becoming more uniformly active as its slow approach to the sun gradually warmed up regions that had previously been frozen solid for eons. Unlike the enigmatic and deeply puzzling first interstellar visitor, this new cosmic wanderer was behaving exactly as astronomers expected an active comet to behave. Every single observation only served to confirm that it was following the same physical laws that govern the comets throughout our own solar system. And yet, the very normality of its behavior carried with it the most profound implications for our understanding of how planetary systems form and evolve all across our galaxy. The sheer difference in scale between the two well-studied interstellar visitors reveals just how much we missed, how much we couldn't know, with that first mysterious wanderer. While astronomers were never able to determine the exact size of the first elongated visitor, Oumuamua, the best estimates suggested it measured somewhere between 300 and 3,000 feet in length. To visualize this, picture a large skyscraper, perhaps the height of the Eiffel Tower, but stretched out into the shape of a cosmic needle, tumbling silently through space. That object was already at the absolute limit of what our most powerful telescopes could detect as it raced away from our solar system, fading with every passing moment. This new interstellar comet, by stark contrast, completely dwarfs its predecessor by orders of magnitude. Early estimates, based on its brightness and level of activity, suggest its solid nucleus is several miles across. This would make it roughly 100 times more massive than the first visitor. To put this into a more relatable perspective, imagine comparing the size and mass of a school bus to that of a small city. The immense difference in size translates directly into a vastly greater observational opportunity, giving astronomers enormously more material to study and analyze. This larger size is the primary reason why this comet can produce such a spectacular and easily observable display of activity. With a much greater surface area exposed to the sun's heating, and with vastly more ice available for sublimation, the comet can generate the bright, expansive coma and the long, visible tail that make it detectable by telescopes all around the world. The first visitor, Oumuamua, even if it did contain some ice, was simply too small, too compact, to produce a level of outgassing that would be detectable from Earth under most circumstances. An object's size also determines how long it remains observable. The first interstellar wanderer, Oumuamua, faded from view within a few months of its discovery, becoming too faint for even the largest telescopes on Earth to track. This new comet, however, with its substantial multi-mile nucleus and its large, active coma, will remain visible to ground-based telescopes for many months, perhaps even over a year, allowing for a much more extensive and detailed study of its composition and its long-term behavior. The difference in mass also fundamentally affects how the two objects respond to the subtle non-gravitational forces in space, like solar radiation pressure. The first visitor's small size and potentially very low density made it susceptible to forces that would barely influence larger, more massive objects. The gentle pressure of sunlight, the solar wind, and even interactions with the sun's magnetic field could have potentially altered its trajectory in measurable ways, contributing to the puzzle of its motion. This new, much more massive comet, on the other hand, follows a much more predictable path, one that is determined almost exclusively by the familiar and well-understood force of gravity. The substantial size of this interstellar comet also provides crucial information about the planetary system that ejected it out into interstellar space. Large comets like this one require significant reservoirs of ice and dust to form in the first place, which suggests that they originate from planetary systems that had substantial, massive debris disks during the early stages of their planet formation. The very existence of such large interstellar objects hints that planetary systems capable of forming substantial comet populations, much like our own Oort cloud, may be quite common throughout the galaxy. Moreover, the size of the object affects how deeply cosmic radiation can influence it during its long interstellar journey. Larger objects are able to retain more of their original, primordial composition in their deep interiors, which are shielded from the relentless effects of cosmic rays that gradually alter the surface materials over millions of years. This excellent preservation means that spectroscopic studies of the material outgassing from this comet could reveal relatively uncontaminated, pristine samples of the raw materials from its birth environment. This dramatic size difference between our two most famous interstellar visitors also raises intriguing questions about the selection effects that are inherent in our observations. Are we currently seeing a truly representative sample of the interstellar objects that pass through our solar system, or are we just seeing the very tip of a vast cosmic iceberg? When the Atlas network first detected this new interstellar comet, it was traveling at a breathtaking 137,000 miles per hour relative to our solar system. That velocity translates to 38 miles for every single second that passes. This is a speed fast enough to cross the entire continental United States in less than 2.5 minutes. To try and comprehend this cosmic speed, imagine once again standing beside a highway where cars are traveling at a brisk 70 miles per hour. This interstellar visitor would flash past you nearly 2,000 times faster than that highway traffic. It would cover the distance from New York to Los Angeles in the time it takes you to brew a morning cup of coffee. But speed, in the frictionless environment of space, behaves differently than speed on Earth. As the comet falls deeper and deeper into our sun's immense gravitational well, it accelerates dramatically. In the same way that a marble speeds up when it is rolling downhill, this cosmic wanderer continuously gains velocity as it gets closer to the sun. By the time it reaches its closest approach to the sun in late October, the comet will be racing at a truly staggering speed of over 160,000 miles per hour. This constant acceleration is a powerful demonstration of the immense gravitational power of our star. The sun's gravity reaches out across billions of miles of space, gently but inexorably tugging on this interstellar visitor, bending its path from what was a nearly straight line into a graceful, open-ended, hyperbolic curve. The comet arrived from the depths of interstellar space on a nearly straight trajectory, but the sun's powerful influence has gradually and beautifully curved its path, and it will eventually swing around our star like a cosmic slingshot before being flung back out into the galaxy. This extreme velocity creates a unique set of challenges that astronomers rarely face when they are studying the more sedate, normal objects of our solar system. Most comets and asteroids move relatively slowly across the night sky, allowing telescopes to track them for hours or even days at a time using the same instrument settings. This interstellar speedster, however, races across a telescope's field of view so quickly that observers must be constantly and precisely adjusting their pointing and tracking systems just to keep it centered in the frame. The sophisticated tracking systems of professional telescopes, which are designed to follow the slow, predictable motions of the stars, struggle to keep pace with this cosmic sprinter. The object moves fast enough that the exposure times for images must be carefully and precisely calculated to prevent the comet itself from creating long, blurry streaks across the detector during long observations. Astronomers are forced to balance the critical need for long exposures to gather the faint light from the comet against the rapid motion that would otherwise blur their precious images into uselessness. The high velocity also compresses the window of observation dramatically. Unlike the periodic comets like Halley's Comet that return to our skies every few years or decades, providing multiple opportunities for study over the centuries, this visitor will pass through our solar system exactly once. When it departs, it will carry its ancient secrets with it back into the unimaginable depths of interstellar space, never to return to our vicinity in the lifetime of our species or even our planet. The speed differential between our own solar system and this interstellar wanderer also reveals something profound about the nature of galactic motion itself. Our entire solar system is orbiting the center of the Milky Way galaxy at a speed of about 500,000 miles per hour. But this comet arrived from a different part of the galaxy, with its own different orbital velocity around the galactic center. The collision, so to speak, of these two different cosmic reference frames is what creates the high relative motion that makes interstellar objects so distinctive and easy to identify. Understanding these velocities with great precision helps astronomers to trace the object's path back toward its possible region of origin, and also to project its path forward to its future, distant destination. After its brief, fleeting encounter with our Sun, this cosmic messenger will resume its lonely journey into the vast, silent darkness between the stars, a journey without end. Every single photon of light, every faint particle of electromagnetic radiation that is reflected from this interstellar comet, is a time capsule. It carries information that has traveled across the vast expanse of the galaxy for millions of years. When astronomers aim the powerful spectrographs of their telescopes at the comet's glowing coma, they are, in essence, performing remote chemistry experiments on materials that were formed in the swirling protoplanetary disk around a distant, unknown star. Each element and each molecule within the coma absorbs and emits light at its own specific, characteristic wavelengths. This process creates a unique, intricate pattern of bright and dark lines in the spectrum of the comet's light, a pattern that serves as an unmistakable fingerprint, revealing the precise composition of the gas and dust that is streaming away from the comet's nucleus. These spectroscopic signatures are like a form of cosmic DNA, carrying the fundamental chemical code of another planetary system. The initial spectroscopic observations of this new comet have revealed a mixture of both familiar and surprising elements within its coma. Water vapor showed up almost immediately in the data, confirming that H2O ice is a common building block that forms around other stars, just as it does in the primordial cloud that formed our own solar system. Carbon monoxide and carbon dioxide also appeared in the expected ratios, which suggests that the basic chemistry of comet formation operates in a remarkably similar fashion across many different stellar environments. But it is the subtle, almost imperceptible differences in the isotopic ratios that tell a much more complex and fascinating story. Isotopes are different versions of the same chemical element that have a different number of neutrons in their nuclei. The ratio of different oxygen isotopes, for example, is highly dependent on the specific physical conditions that were present when the comet first formed billions of years ago. These ratios act as a kind of cosmic birth certificate, revealing fine details about the temperature, the pressure, and the raw materials that were available in the original stellar nebula from which this comet was born. The deuterium to hydrogen ratio found in the water vapor provides particularly valuable and sought-after information. Deuterium is a heavy isotope of hydrogen, containing 1 proton and 1 neutron in its nucleus, instead of just a single proton. The amount of deuterium that gets incorporated into water ice is highly dependent on the temperature and density conditions during the formation process. By precisely measuring this ratio, astronomers can estimate whether the comet formed in the warmer inner regions of its original planetary system or in the cold, frigid outer reaches, where most comets are believed to be born. The early measurements of 3I suggest that this interstellar visitor formed in conditions that were very similar to those found in the outer regions of our own early solar system. Its chemical signatures most closely match those of the comets that originate from our own Kuiper belt, the vast reservoir of icy bodies that orbits the Sun out beyond the path of Neptune. This remarkable similarity suggests that the fundamental processes of planetary system formation may be surprisingly consistent across many different types of stars. However, some of the trace elements detected in its coma show intriguing and significant differences from the norms of our solar system. The relative abundance of certain metals found within the coma's dust particles hints that the comet's parent star had a slightly different chemical composition than our own Sun. Stars that are formed from gas clouds that have been enriched by previous generations of stellar explosions can have higher concentrations of heavy elements, and these subtle differences in the stellar chemistry get incorporated into the planets and comets that form around them. The organic compounds that have been detected in the coma present the most tantalizing and profound possibilities. Simple carbon-based molecules like formaldehyde and methanol are known to be common in comets throughout our own solar system. But it is possible that this interstellar visitor may carry a more complex and diverse suite of organic chemistry. Advanced spectroscopic techniques may be able to identify more complex molecular structures, revealing the pathways of chemical evolution that occurred in its distant birth environment. These chemical signatures provide us with our first direct, physical samples of the raw materials from another planetary system, offering insights that would otherwise require us to undertake the impossible journey of interstellar travel just to obtain them. But the beautiful, ethereal tale of this cosmic visitor tells an even more detailed and dynamic story about the conditions in its distant, long-lost home. The graceful, glowing tale that is now streaming from this interstellar comet is far more than just a beautiful celestial display. It is, in a very real sense, a time machine, carrying dynamic, real-time information from another star system across the void. As the solar wind and the pressure of sunlight push gas and dust away from the comet's nucleus, it creates two distinct and separate types of tails, each of which reveals different aspects of the object's composition, its history, and its interaction with our Sun. The ion tail, which is made of electrically charged gas molecules, or ions, glows with a characteristic bluish light and points almost directly away from the Sun, acting like a cosmic windsock, showing the precise direction of the solar wind. The dust tail, which is typically broader and more curved, follows a slightly different path, one that is shaped by the delicate balance between the outward pressure of solar radiation and the comet's own orbital motion. The ion tail provides a real-time chemical analysis of the various gases that are being released from the nucleus. As the intense ultraviolet radiation from the Sun strips electrons from the gas molecules, It creates glowing ions that emit light at very specific, characteristic wavelengths. Sodium ions, if present, would glow with a distinct yellow light. Carbon monoxide ions appear as a vibrant blue, and water ions shine with a distinctive blue-green hue. This process of natural spectroscopy reveals not just what elements and molecules are present in the comet's ice, but also their relative abundances. The dust tail, on the other hand, tells a different story. It speaks of the solid materials, the primordial dust grains, that were incorporated into the comet when it first formed billions of years ago. A microscopic analysis of the sunlight that is scattered by these tiny dust particles can reveal their size distribution, their composition, and even their physical structure. Unlike the gas molecules, which can be altered by chemical reactions during the comet's long journey through space, the solid dust grains preserve a much more direct and pristine record of the conditions that existed in the original stellar nebula. The ratio between the gas and dust production rates is another crucial piece of the puzzle, as it indicates how the comet formed and evolved in its birth environment. Comets that formed closer to their parent star tend to have a lower ice content and therefore produce less gas relative to the amount of dust they release. Those comets that formed in the cold, outer regions of planetary systems are typically much more ice-rich and are capable of generating spectacular gas tails when they approach a star. The preliminary observations of 3 suggest that this interstellar comet has a gas-to-dust ratio that is very similar to the long-period comets that originate from our own solar system's distant Oort cloud. This striking similarity implies that this visitor also formed in the frigid outer reaches of its original planetary system, where temperatures were low enough for the most volatile ices to condense and accumulate on the surfaces of solid dust grains. The tail can also reveal information about the magnetic environment that existed around the comet's parent star during the era of planet formation. Different stellar magnetic field strengths can influence how the primordial dust grains clump together and grow into larger bodies. The size distribution of the dust particles that are being shed into the tail today still carries the faint signatures of these ancient magnetic processes from billions of years ago. As the comet continues its steady approach toward the Sun, its tail will grow longer, brighter, and more spectacular. The increasing solar heating will begin to sublimate ice from the deeper layers of its nucleus, potentially revealing materials that have been kept in a perfect, deep-frozen state since the comet's formation. These pristine primordial materials could contain complex organic molecules or mineral structures that would provide direct, unambiguous evidence of the chemical conditions in another stellar system. The evolution of the tail over time will also help to constrain the models of how the comet has changed and been weathered during its millions of years spent in interstellar space. While cosmic radiation has gradually altered the surface materials, the deep interior has remained largely unaffected. As the Sun's heat penetrates deeper and deeper into the nucleus, astronomers are essentially able to peel back the layers of time, studying materials that represent different epochs in the comet's long and incredible history. The ability to study an active interstellar comet in such detail represents an unprecedented and revolutionary opportunity in planetary science. Never before have we been able to track these dynamic, beautiful processes in real time for an object that we know originated around another star. Following an interstellar comet across the night sky requires telescope technology and observational techniques that are pushed to their absolute limits. The fastest military sniper bullets travel at a speed of about 3,000 feet per second. This interstellar comet is moving at approximately 200,000 feet per second, making it roughly 67 times faster than a speeding bullet. But unlike a bullet, which travels in a more or less straight line for a few seconds, this cosmic projectile is following a curved path across our sky for many months, requiring constant, precise, and complex adjustments just to keep it within the tiny field of view of a powerful telescope. Modern professional telescopes use incredibly sophisticated computer-controlled mounting systems to track moving objects. The telescope's control system calculates the object's predicted position thousands of times every second, making thousands of tiny, microscopic adjustments to the telescope's motors to counteract the Earth's own rotation and the target's independent motion through space. For most asteroids and comets within our solar system, this kind of tracking is a routine, if complex, procedure. For interstellar objects moving at such extreme speeds, it pushes these advanced systems to their absolute engineering limits. The challenge begins with the fundamental task of determining exactly where the comet will be from one night to the next, or even from 1 hour to the next. Normal solar system objects follow predictable, closed elliptical orbits that astronomers can calculate with exquisite precision, sometimes years or even decades in advance. Interstellar objects, however, follow open-ended hyperbolic trajectories that are inherently more difficult to predict, especially when the subtle, unpredictable outgassing from the nucleus is creating small but measurable changes to that orbit. Professional observatories around the world must coordinate their observations with meticulous care to maximize the scientific return as the comet races across different parts of the sky. When the object sets below the horizon at an observatory in Chile, telescopes on the other side of the Earth, in Hawaii or Australia, are ready to take over the watch. This global, non-stop relay ensures continuous monitoring of the comet, despite the Earth's rotation and the comet's own rapid motion. Advanced imaging techniques are employed to extract the maximum amount of information from each and every observation. Rather than taking single, very long exposures, which would cause the fast-moving comet to appear as a long, blurry streak, astronomers instead capture a series of many shorter images. These individual images can then be combined mathematically using a technique called shift and stack processing to enhance the faint details of the comet. This clever technique allows the comet to remain sharp and in focus, while the background stars, which are stationary, are blurred into long streaks. The most sophisticated observatories in the world can track these moving objects so precisely that they can maintain a perfect focus on targets traveling at interstellar speeds for hours at a time. The Hubble Space Telescope, orbiting high above the blurring effects of Earth's atmosphere, has achieved some of the sharpest, most detailed images ever obtained of an interstellar object by using this advanced tracking capability. Radio telescopes face even greater challenges when they attempt to study these fleeting interstellar visitors. Radio observations require extremely precise pointing accuracy, often measured in fractions of an arcsecond, which is an impossibly small angle on the sky. The combination of the object's own rapid motion and the Earth's rotation means that radio telescopes must constantly and perfectly adjust their pointing, while also maintaining the precise frequency tuning needed to detect the incredibly faint radio signals that might be emitted by certain molecules in the coma. The Doppler effect adds another layer of profound complexity to these radio observations. As the comet moves toward or away from the Earth at tens of miles per second, it shifts the frequency of any radio signals it might be emitting by amounts that can overwhelm the very narrow frequency ranges used by the sensitive radio receivers. Astronomers must therefore continuously adjust their receiver frequencies in real time to perfectly compensate for this cosmic Doppler shift. Despite these immense challenges, the global astronomy community has developed an unprecedented level of coordination in tracking this interstellar visitor. Observations from ground-based telescopes, space-based observatories, and even dedicated amateur astronomers are all contributing to a single, comprehensive picture of the comet's behavior and its chemical composition. This massive, coordinated effort will reach its dramatic climax as the comet approaches its closest point to our Sun in the final days of October. October 30th, 2025, will mark the most dramatic and significant moment in this interstellar comet's billion-year journey. On that specific date, this cosmic wanderer will reach perihelion, which is its closest point of approach to our Sun, at a distance of approximately 130 million miles. This places it just inside the orbit of the planet Mars, which is close enough for the Sun's intense, focused radiation to drive spectacular and violent activity from the comet's ancient icy nucleus. For comparison, this is about 40% closer to the Sun than the Earth's average distance, which will subject the comet to a level of solar heating that is nearly 3 times more intense than what our own planet receives. This close approach to perihelion will transform this already active comet into a true cosmic spectacular. As the Sun's powerful heat penetrates deeper and deeper into the nucleus, it will begin to sublimate ices that have remained in a deep, pristine freeze since the comet's formation around another star, billions of years ago. This fresh, primordial ice, which has been protected by the outer layers of the comet during its long, cold interstellar journey, may contain unique materials that will reveal the original, unaltered chemistry of the comet's distant birth environment. The vastly increased activity will cause the comet's tail to grow dramatically longer and brighter. Current models predict that the tail could extend for millions of miles across space, potentially making the comet itself visible to dedicated amateur astronomers with modest, backyard telescopes, despite the comet's enormous distance from the Earth. This spectacle will offer a rare and valuable opportunity for citizen scientists around the world to contribute meaningful observations of an object that originated in another star system. However, the intense solar heating that drives this activity also creates significant observational challenges. As the comet approaches its perihelion, it will also be moving closer to the Sun's position in Earth's sky, which will make it increasingly difficult to observe from the ground. The bright, overwhelming glare of the Sun will eventually overwhelm the comet's faint light, forcing astronomers to suspend their ground-based observations until the object emerges on the far side of the Sun in early December. This period, known as solar conjunction, represents a critical and frustrating gap in the observational coverage, and it is occurring at precisely the time when the comet is at its most active and most interesting phase. Space-based observatories, however, like the Solar and Heliospheric Observatory, SOHO, which are specifically designed to study the Sun's corona, may be able to capture images of the comet even during this close passage. These specialized instruments are equipped with coronagraphs that can block out the Sun's blindingly bright disk while still observing the surrounding space where the comet will be traveling. The powerful gravitational effects of the Sun's proximity will also be bending the comet's trajectory most dramatically during its perihelion passage. The open-ended hyperbolic orbit that brought this visitor from interstellar space will be significantly modified by the Sun's gravity, which will potentially change the comet's future path through the galaxy in subtle ways. Precise measurements of the comet's position during this critical phase will help astronomers to predict its ultimate destination after it leaves our solar system. The extreme solar heating may also reveal important structural information about the comet's nucleus. If the nucleus contains significant amounts of more volatile ices, like frozen carbon monoxide or nitrogen, they will sublimate explosively near perihelion, which could potentially cause the nucleus to fragment or create dramatic, unpredictable outbursts of activity. Such events, if they occur, would provide unique and invaluable insights into the internal structure and composition of this interstellar visitor. For planetary scientists, The perihelion passage represents the peak opportunity, the single most important moment, to study how materials from another star system respond to the intense radiation of our own sun. The detailed comparison between this comet's behavior and that of our native solar system comets could reveal fundamental differences in their composition or their structure, differences that would reflect their different formation environments. As perihelion approaches, telescopes all around the world will maintain a continuous, unbroken surveillance of this unique cosmic visitor. The wealth of observations gathered during these crucial weeks will provide the most detailed and comprehensive portrait ever obtained of an active interstellar object. Unlike the predictable, familiar comets that grace our skies every few years or decades, this interstellar visitor is making a once-in-forever appearance. The profound difference lies in the fundamental, geometric nature of its orbit. Most of the comets that belong to our solar system follow closed, elliptical paths that bring them back to the inner solar system again and again, repeatedly. Halley's Comet, for example, famously returns every 76 years. The magnificent comet Hale-Bopp visits us roughly every 500 years. These are the periodic comets, and they are gravitationally bound to our sun, trapped in endless, looping paths that have continued for millions, and in some cases billions, of years. This interstellar comet, however, is following a hyperbolic trajectory. This is a mathematical curve that approaches the sun just once and then diverges, heading back out into infinity, never to cross paths with our star again. To visualize this, picture throwing a ball at a wall. An elliptical orbit is like a ball that is attached to the wall by a rubber band. It stretches out and contracts, but it always returns to its starting point. A hyperbolic orbit, on the other hand, is like a ball that is thrown so hard that it bounces off the wall and flies away forever, never to return. The comet's excessive, incredible speed is the key to understanding its trajectory. At 137,000 miles per hour, it is carrying far more kinetic energy than the sun's powerful gravity can ever hope to permanently capture. Our star can certainly bend the comet's path, and it will even accelerate it during its close passage, but it cannot slow the visitor down enough to trap it in a closed, repeating orbit. The comet will swing around the sun like a cosmic slingshot, gaining some energy in the process, and then head back out into the unfathomable depths of interstellar space. After its dramatic perihelion passage in late October, the comet will begin its eternal journey away from our solar system. It will first cross the orbit of Mars in November, then the orbit of Jupiter in early 2026. By 2028, it will pass beyond the majestic rings of Saturn, entering the cold, dark, outer reaches of our solar system, where the sunlight becomes too faint to drive any significant cometary activity. The comet will continue its journey outward for thousands of years, gradually fading from view as it moves farther and farther from the sun's warming influence. Eventually, it will cross the heliopause, the theoretical boundary, where the solar wind from our sun finally gives way to the true interstellar medium. At that point, which will be roughly 100 years from now, it will officially return to interstellar space, carrying with it the subtle chemical and physical changes that were caused by its brief, violent encounter with our sun. During its passage through our solar system, the comet will have lost a tiny fraction of its total mass through the process of sublimation. This material, this dust and gas from another star, will remain behind, adding microscopic amounts of interstellar material to our own solar system's inventory. In a very real sense, our sun will have permanently captured a tiny, precious sample of matter from another star system. Even as the main body of the comet escapes back into the galaxy, the gravitational interaction with our sun will also have slightly, but permanently, modified the comet's future trajectory through the galaxy. While the change will be small, it means that the comet will now follow a different path than it would have if it had never encountered our solar system. In millions of years, this tiny deflection could be the difference that determines which star system the comet visits next, if it ever visits one at all. The absolute, one-way nature of this incredible encounter is what makes every single observation so critically precious. Unlike the periodic comets that offer us multiple opportunities for study over centuries or even millennia, astronomers have only this one single chance to learn everything that is possible to learn about this interstellar messenger. Once it departs, it is highly unlikely that human civilization will ever see this particular object again, making the current observations a unique, irreplaceable window into the workings of another stellar system. The Atlas telescopes perceive a universe that is almost entirely invisible to human vision. They are designed to detect cosmic wanderers that are far too faint for any earthbound human observer to ever notice. The human eye, a marvel of biological evolution, can see stars down to about the 6th magnitude, and only under perfect, dark sky conditions, far from the light pollution of cities. This represents the sensitivity limit that was evolved over millions of years for the purpose of spotting predators and prey on the African savanna, not for hunting faint, dark cosmic visitors that are traveling between the star systems. The Atlas cameras, by comparison, can routinely reach a magnitude of 20. This means they can detect objects that are 100,000 times fainter than the dimmest stars that are visible to the naked eye. To understand this profound difference in sensitivity, imagine trying to spot a single match flame. With your unaided eyes, on a clear, dark night, you might be able to see it from across a football field. The Atlas system, with its electronic eyes, could detect that very same match flame from over 3,000 miles away, which is roughly the distance from New York to Los Angeles. This extraordinary sensitivity is achieved by combining large, highly efficient digital sensors with precise, wide-field optics and extremely sophisticated computer processing. Each Atlas telescope captures light for a full 30 seconds in every single exposure, allowing it to accumulate the faint photons from distant objects that would be completely invisible in shorter glimpses. The human eye, by contrast, integrates light for only about 1/30th of a second before resetting itself, which makes it physically impossible to build up enough of a signal to see these incredibly dim cosmic visitors. The electronic detectors in the Atlas cameras can effectively store light indefinitely, building up detailed images of objects that are millions of times too faint for our biological vision to perceive. The wavelength sensitivity of the Atlas system also extends beyond the range of human perception into the near-infrared part of the spectrum. While our eyes can only detect the visible light that ranges from blue through red, the Atlas cameras are also responsive to the longer wavelengths that are associated with the heat radiation emitted by warm objects. This infrared sensitivity allows the system to detect certain types of asteroids and comets by their own thermal emission, even when they are very dark and reflect very little sunlight. The computer processing behind the scenes amplifies these capabilities even further. The custom-built Atlas software automatically and meticulously compares each new image against vast reference catalogs that contain the precise positions of millions of known stars and galaxies. Any object that appears in a new position that is not in the reference catalog is immediately flagged for further analysis. This automated digital comparison happens within minutes of each exposure being taken, allowing the system to identify moving objects in real time as they travel across the sky. The system's temporal resolution provides another critical advantage over human perception. By taking 4 separate images of each region of the sky, separated by 10-minute intervals, Atlas can detect motion that would be completely imperceptible to a human observer. A typical asteroid moving at normal speeds will only cover a few arcseconds of the sky in 10 minutes, which is an angular distance that is smaller than the apparent size of a grain of sand when viewed from 100 feet away. Atlas also perceives the sky in specific wavelengths of light that have been selected to be optimal for asteroid detection. The system uses special filters that enhance the contrast between the reflected light of asteroids and the natural background glow of the sky, making these faint objects much more detectable than they would be in natural, unfiltered sunlight. These specialized filters effectively remove much of the atmospheric airglow that limits ground-based observations, which in turn gives the telescopes much cleaner, clearer views of space. The global network effect then multiplies these individual capabilities into a formidable whole. While a single human observer can only ever see one hemisphere of the sky at any given time, the 4 Atlas stations, working together, are able to monitor the entire dark sky every 24 hours. This continuous, unbroken coverage ensures that no potentially threatening object can approach our planet from any direction without being detected. And perhaps most importantly of all, Atlas never sleeps, it never gets tired, and it never loses its concentration. These robotic sentinels maintain their silent, tireless vigil every single clear night, scanning the cosmos with an inhuman persistence, patiently waiting for the next visitor from the stars. The 4 Atlas telescopes, separated by thousands of miles of ocean and continent, operate as a single, coordinated organism. Each individual station contributes its data to a collective intelligence that is far greater than the sum of its parts. When the Chilean telescope, for example, detects a new moving object, the powerful computers at all 4 sites immediately receive the discovery data. Within minutes, the other telescopes in the network can be commanded to point toward the same region of the sky to gather crucial, confirming observations. This rapid automated cross-verification is essential for eliminating the false alarms that can be caused by cosmic ray hits on the detector, the trails of passing satellites, or other instrumental artifacts that might fool a single, isolated telescope. The global distribution of the telescopes creates overlapping fields of view that provide multiple simultaneous perspectives on the same cosmic events. When an object appears very low on the horizon for one telescope, where the view is blurred by the thick atmosphere, it may be perfectly positioned high in the sky for detailed observations by another station that is thousands of miles away. This valuable geographic diversity ensures that localized atmospheric conditions, bad weather, or even technical problems at one of the sites do not interrupt the continuous monitoring of important and time-sensitive discoveries. Each telescope also contributes its own unique observational advantages to the collective effort. The 2 Hawaiian stations, for example, benefit from the exceptionally stable atmospheric conditions that are found high above the Pacific Ocean, which allows them to provide the steadiest, sharpest images for making precise position measurements. The South African telescope operates in one of the world's driest climates, which minimizes the atmospheric absorption of light that can dim the very faintest objects. The Chilean site sits at a very high altitude in the Atacama Desert, a place where the crystal-clear skies allow for the detection of the faintest possible targets. The separation of the sites by time zone provides perhaps the most crucial advantage of the global network. As the Earth's rotation carries one telescope into the daylight, rendering it useless for observation, other telescopes in the network are just entering the deep darkness of their prime observing hours. A threatening asteroid that is discovered in the morning twilight at one site can be immediately handed off and tracked by telescopes that are just beginning their evening observing sessions on the other side of the world. This seamless 24-hour coverage effectively eliminates the dangerous gaps in our surveillance that plagued earlier sky survey systems. The data processing for the network occurs simultaneously at all of the sites, with sophisticated, custom-built algorithms comparing the observations from across the entire network in real time. If one telescope detects an object that is moving at a very high angular velocity, the system can automatically alert the other telescopes to search for the same target in their current or upcoming observations. This highly coordinated response dramatically improves the chances of successfully tracking very fast-moving objects that might otherwise be quickly lost. The distributed architecture of the network also provides crucial redundancy for the critical mission of protecting the Earth from asteroid impacts. If a large asteroid were to be discovered on a direct collision course with Earth, the loss of any single telescope in the network due to weather, equipment failure, or any other problem would not interrupt the continuous tracking that is needed for accurate impact prediction. The remaining telescopes in the network could still maintain sufficient observations to refine the object's orbit and predict the impact location and timing with great accuracy. The communication between the various sites happens through dedicated, high-speed internet connections that ensure that the observation data reaches all of the telescopes within seconds of being captured. Advanced data compression algorithms are used to minimize the bandwidth that is required to share the enormous volumes of data that are generated each night, which allows for this real-time coordination despite the vast distances that separate the stations. The collective intelligence of the Atlas network extends beyond simple detection to the much more complex task of sophisticated orbit determination. By combining the observations from multiple sites, which are taken at slightly different times and from slightly different viewing angles, the system can calculate preliminary orbits for new discoveries within a matter of hours, instead of the days or even weeks that were required by the single telescope surveys of the past. This powerful networked approach has completely revolutionized humanity's ability to monitor the constant threats from space and to discover the rare and precious visitors from other star systems. This coordinated, global surveillance represents our species' most advanced and most effective early warning system for all manner of cosmic hazards. Every clear night, this coordinated network of robotic guardians scans the cosmos for objects that could pose a threat to human civilization. But Atlas represents just one crucial component of humanity's growing and increasingly sophisticated planetary defense infrastructure. The system works in close partnership with other major sky surveys, such as NASA's Catalina Sky Survey in Arizona, the Linear Project in New Mexico, and the NEOWISE Space Telescope, which orbits the Earth. Together, these powerful surveys create a multi-layered, overlapping coverage of the sky that ensures no significant threat can approach our planet completely undetected. As a collective, these surveys have now successfully cataloged over 90% of the near-Earth asteroids that are larger than 1 kilometer across. These are the dinosaur killer-sized objects, and this comprehensive catalog has essentially eliminated the risk of a surprise, civilization-ending impact from a known object. The warning times that are provided by this global network scale, with the size of the object, in ways that are designed to match our current defensive capabilities. A massive 2-mile-wide asteroid, one that would be capable of causing a global catastrophe, would be detected decades before a potential impact, which would provide more than ample time for humanity to develop and deploy a series of deflection missions. A smaller, 300-foot asteroid, one that would be large enough to completely devastate a major metropolitan area, would receive several weeks of warning. Even the smaller, 60-foot Chelyabinsk-sized objects that could cause significant damage to cities would be spotted days in advance, allowing for evacuations. These warning times are designed to align with humanity's emerging asteroid deflection technologies. NASA's recent DART mission successfully and spectacularly demonstrated that a spacecraft impact can indeed alter an asteroid's trajectory, proving that we now possess the basic, fundamental technology that is needed to defend the Earth from many cosmic threats. The European Space Agency's follow-up Hera mission will provide detailed observations of the aftermath of the DART impact, which will help to refine our understanding of how to deflect dangerous asteroids in the most effective and predictable way. The detection network also supports the rapid response protocols that could save millions of lives, even in a scenario where deflection is not possible. For small asteroids that might be on a trajectory to impact a populated area, the precise tracking provided by the network allows authorities to predict the impact location to within a few square miles. This incredible accuracy enables the targeted evacuation of the most dangerous zones, while avoiding unnecessary panic in the surrounding regions. Atlas contributes its own crucial and unique capabilities to this defensive network through its specialized focus on these last-minute detections. While the other, larger surveys excel at finding the big objects years in advance, Atlas fills the critical gap for the smaller, more numerous threats that might appear suddenly. The system's unique ability to scan the entire sky every single night ensures that even those objects that are approaching from previously unmonitored directions, like from the direction of the Sun, cannot achieve complete surprise. This global coordination extends beyond just the telescopes themselves to include sophisticated orbit calculation centers that process the discovery data from all surveys in real time. The Minor Planet Center, which is hosted at the Smithsonian Astrophysical Observatory, serves as the official international clearinghouse for all asteroid discoveries. It collects the observations from surveys worldwide and calculates precise orbits for new objects within hours of their detection. NASA's Planetary Defense Coordination Office maintains a continuous liaison with international space agencies, military organizations, and emergency management authorities to ensure that any information about a potential asteroid threat reaches the key decision-makers immediately. Automated alert systems can notify key personnel within minutes of the detection of a potentially hazardous object, triggering a series of coordinated response protocols that span multiple nations and organizations. And our detection capabilities continue to improve every single year as new and more powerful telescopes join the global network, and the existing systems receive constant upgrades. The upcoming Vera Rubin Observatory will completely revolutionize the field by being able to detect asteroids that are hundreds of times fainter than even the current surveys can reach. This next-generation facility is expected to discover an estimated 5 million new asteroids during its first decade of operation alone. Future space-based observatories like the planned NEO Surveyor mission will extend our surveillance into the infrared wavelengths and into the sky regions that are inaccessible from the ground. These orbital sentinels will provide the final, crucial pieces that are needed for a truly comprehensive protection of our planet from all manner of cosmic threats. The era of interstellar object discoveries has only just begun. With revolutionary new skies surveys about to transform our ability to detect these faint, fast-moving visitors from other star systems, we are on the cusp of a new understanding of our place in the galaxy. Current theoretical models predict that somewhere between 1 and 10,000 interstellar objects are passing through our solar system at any given time. The vast majority of these cosmic wanderers remain in the cold, dark outer reaches of our system, far beyond the orbit of Neptune, and they are much too distant and too faint for our current generation of telescopes to detect. But as our survey capabilities improve exponentially in the coming years, we will begin to find these elusive visitors in truly unprecedented numbers. The Vera Rubin Observatory, which is currently nearing completion high in the Chilean Andes, will completely revolutionize the field of interstellar object detection with its unprecedented combination of extreme sensitivity and a vast field of view. This next-generation facility will be able to image the entire visible sky from its location every 3 nights, and it will be able to reach objects that are hundreds of times fainter than even the powerful Atlas survey can detect. The current computer models suggest that the Rubin Observatory will discover between 1 and 3 new interstellar objects every single year. This will allow us to build up a true statistical sample of these objects, which will transform our understanding of these cosmic messengers from a study of oddities to a true science. Each new discovery will add another crucial piece to a cosmic puzzle that spans the entire galaxy. Some of these interstellar objects will arrive from the direction of nearby star systems, which may allow astronomers to trace them all the way back to their specific star of origin. Others will carry exotic chemical signatures that will reveal the composition of stellar environments that are hundreds or even thousands of light years away. The accumulated data from these discoveries will allow us to create the first comprehensive map of the material exchange that is happening between the star systems in our local galactic neighborhood. Future surveys will also be able to detect much smaller interstellar objects than our current capabilities allow. While the first few discoveries have involved objects that are hundreds of feet to several miles across, the improved telescopes of the near future will be able to find visitors that are as small as cars or even houses. These tiny fragments may represent chips that have been knocked off larger bodies by cosmic collisions, and they could be carrying invaluable samples of planetary surfaces or even the deep cores of asteroids from distant, alien worlds. The James Webb Space Telescope and the upcoming generation of extremely large telescopes on the ground will provide unprecedented spectroscopic capabilities for studying these interstellar visitors in exquisite detail. These incredibly powerful instruments will be able to detect trace organic compounds and exotic ices that will reveal the complex pathways of chemical evolution that are occurring in other stellar environments. Such detailed studies could even, in the distant future, identify potential biosignatures, the chemical indicators of life that have been preserved in interstellar objects that have been ejected from biologically active worlds. Specialized space missions that are designed to actually intercept and study interstellar objects are already in the development stage. The European Space Agency's Comet Interceptor mission, for example, will station a spacecraft at a stable point in space, the L2 Lagrange point, where it will wait patiently, ready to be deployed on a rapid trajectory toward any suitable interstellar visitor that is discovered. Such missions would be able to analyze the surface materials of these objects directly, providing a level of detailed chemical and isotopic information that would be impossible to obtain from ground-based observations. Advanced computational models powered by artificial intelligence will help us to predict when and where new interstellar objects might appear. By better understanding the galactic dynamics that cause objects to be ejected from planetary systems, astronomers may one day be able to forecast the arrival times and trajectories for objects that are coming from specific stellar regions. This predictive capability could enable us to make targeted observations that would capture these interstellar visitors much earlier in their approach to our Sun. The rate of discovery will accelerate dramatically as more space-based observatories join the search. Free from the blurring interference of the atmosphere and able to observe continuously, these orbital telescopes will detect interstellar objects across the entire electromagnetic spectrum. Infrared surveys will find the dark, cold objects that are invisible to optical telescopes, while ultraviolet observations will be able to study the gas emissions from active comets in greater detail. Artificial intelligence and machine learning algorithms will eventually automate much of the discovery and classification process, which will enable these surveys to process vastly larger data sets than human astronomers could ever handle manually. These incredible technological advances will soon usher in a new era, an era where the discovery of interstellar objects becomes a routine and expected event, rather than the extraordinary, once-in-a-lifetime occurrence that it is today. The discovery of visitors from other star systems has fundamentally and permanently altered humanity's understanding of our place in the galaxy and the universal processes that govern the evolution of planetary systems. Before the first interstellar object, Oumuamua, arrived in 2017, all of our knowledge of planetary systems beyond our own came entirely from indirect observations. The discoveries of exoplanets had revealed the existence of thousands of worlds orbiting distant stars, but we could only ever infer their properties from the tiny, almost imperceptible amounts of starlight that they blocked or reflected. Interstellar objects, however, provide us with our first direct, physical samples of the raw materials from these alien worlds. The chemical analysis of these interstellar visitors is revealing that the basic, fundamental processes of planetary formation seem to operate in a remarkably similar fashion across many different stellar environments. The water, the carbon dioxide, and the other common compounds that are being found in interstellar comets are a good match for those that we see in our own solar system. This suggests that the universal laws of physics and chemistry produce surprisingly consistent results, regardless of the type of star or the location within the galaxy. However, the subtle but significant differences in the isotopic ratios and the abundances of trace elements hint at the enormous and wonderful diversity that must exist among the planetary systems of our galaxy. Some interstellar objects appear to carry the chemical signatures of formation around stars that are much richer in heavy elements than our own Sun, while others suggest an origin in the more metal-poor environments that are typical of the galaxy's outer regions. These variations provide crucial constraints for our computer models of how different stellar compositions affect the processes of planet and comet formation. The discovery of interstellar objects also reveals the truly dynamic and chaotic nature of planetary systems throughout the galaxy. It now seems apparent that every star system ejects some fraction of its native asteroids and comets out into interstellar space, primarily through powerful gravitational interactions with its giant planets. This ongoing process of cosmic cross-contamination means that the material that was formed around one star can, eventually, be incorporated into other, newly forming planetary systems. This could potentially be a mechanism for spreading the fundamental chemical ingredients for life across vast galactic distances. The size distribution and the arrival rates of these interstellar objects are helping us to constrain our models of planetary system architecture throughout the galaxy. The fact that we have already detected several kilometer-sized interstellar visitors suggests that large comet reservoirs, similar to our own Oort cloud, may be very common features of mature planetary systems. The apparent absence, so far, of planet-sized interstellar objects implies that the gravitational ejection mechanisms that are at play primarily affect the smaller bodies in a system. The statistical analysis of the trajectories of interstellar objects is providing us with new insights into the structure and the dynamics of our own local galactic neighborhood. The directions from which these visitors arrive seem to reflect the orbital motions of the nearby star systems and the large-scale gravitational influences of massive stellar structures like star clusters and nebulae. Future discoveries may reveal complex patterns that will help us to map the large-scale organization of matter in our particular region of the galaxy. The study of interstellar objects has also highlighted the significant gaps that still exist in our understanding of how small bodies evolve over immense cosmic timescales. The mysterious acceleration of the first visitor, Oumuamua, directly challenged our conventional models of how objects behave during their million-year-long journeys through the hostile environment of interstellar space. These surprising discoveries are forcing scientists to consider new physical processes and new chemical reactions that may only operate under the extreme, unique conditions of interstellar travel. And perhaps most profoundly of all, interstellar objects have demonstrated that our solar system exists within a dynamic, living galactic ecosystem, one where material is constantly flowing between the star systems. The traditional view of planetary systems as being isolated, lonely islands in the vast emptiness of space has now given way to the recognition that they are all interconnected nodes in a vast, galaxy-wide network of chemical and physical exchange. This new and powerful perspective suggests that life itself, if it exists elsewhere in the galaxy, may have natural mechanisms for spreading between the star systems. Interstellar objects could, in theory, serve as the natural vehicles for transporting complex organic compounds or even dormant microorganisms across the vast, almost unimaginable distances that separate the stars. The incredible journey of discovery, from the deeply mysterious first interstellar visitor to today's sophisticated global detection networks, has revealed profound and humbling truths about our cosmic neighborhood and humanity's place within it. The enigmatic, needle-shaped wanderer of 2017, Oumuamua, taught us that the universe contains objects that are unlike anything in our direct experience. Its bizarre, unexplained acceleration without any visible outgassing directly challenged our fundamental understanding of small body physics and demonstrated that even our most basic, core assumptions about the nature of space rocks could be wrong. The trapped hydrogen gas theory that eventually and elegantly explained its strange behavior showed us how the relentless bombardment of cosmic radiation can transform ordinary water ice into a form of invisible, natural rocket fuel during the million-year-long journeys between the stars. But more importantly, that first visitor revealed just how unprepared we were, as a species, to study such remarkable and fleeting discoveries. The object was already well on its way out of our solar system by the time astronomers had even found it, which provided only a brief, frantic window for observations before it disappeared forever back into the interstellar night. This cosmic near-miss served as a powerful catalyst, a global wake-up call that directly led to the development of the comprehensive sky surveys that are designed to spot any future visitors much, much earlier in their approach. The Atlas network represents humanity's direct response to that wake-up call. By diligently scanning the entire sky every single clear night, these robotic sentinels are now ensuring that no future interstellar visitor will ever again catch us so unprepared. The very system that detected the third interstellar object in July of 2025 exemplifies how a coordinated global surveillance network can transform astronomical discovery from a lucky chance accident into a systematic, predictable exploration of the unknown. The active comet, discovered by Atlas, provides a perfect and beautiful counterpoint to the first, mysterious visitor. Here is an object that is behaving exactly as astronomers expect a comet to behave, perfectly following the well-understood laws of physics, while at the same time carrying within it the priceless chemical signatures of another star system. Its spectacular growing tail and its glowing coma are offering us unprecedented opportunities to study the raw materials that formed around a distant, alien star billions of years ago. Together, these discoveries demonstrate that interstellar objects come in a wide variety of forms, varieties that we are only just beginning to understand. Some may be exotic, unique wanderers, unlike anything in our own solar system. while others will prove that the same fundamental physical processes are operating throughout the entire galaxy. Both types of objects provide invaluable and irreplaceable information about the processes of planetary system formation and evolution on truly cosmic scales. The incredible technological advances that have been driven by the research into interstellar objects will benefit all of astronomy and all of our efforts in planetary defense. The very same networks that are now hunting for these cosmic visitors are also protecting the Earth from potential asteroid impacts. They are discovering supernovae in distant galaxies and tracking the space debris that threatens our vital satellite missions. The computational techniques that have been developed to analyze these faint, fast-moving objects will have applications in fields ranging from medical imaging to the development of autonomous vehicles. Perhaps most significantly of all, these cosmic messengers have permanently changed how we think about our own solar system's place within the wider galaxy. We now understand that vast amounts of material are constantly flowing between the star systems, creating an interconnected, galactic web of chemical exchange that spans the entire Milky Way. Our Sun is an active participant in this cosmic recycling program, both receiving visitors from other stars and contributing its own native asteroids and comets to the vast interstellar population. The story that began with a single, strange visitor racing silently through our solar system has now evolved into a completely new chapter of astronomical discovery. Advanced surveys will soon be detecting interstellar objects on a routine basis, allowing us to build a comprehensive catalog of the materials that have been ejected from planetary systems throughout our local galactic neighborhood. We now stand at the threshold of a new era, an era where the visitors from other star systems will reveal to us the true chemical and physical diversity of the countless worlds that we may never be able to visit directly, bringing the distant cosmos to us, one cosmic wanderer at a time.